Groups of cell bodies in the PNS. Clusters of cell bodies in the CNS.
Nuclei.
Bundles of axons in the CNS. What's another word for tract? Fasciculus. And then tracts, fasciculi. One tract, fasciculus. White column. Talked about this yesterday. White columns in the spinal cord, right? 3 on each side, a posterior, an anterior, and a lateral. What was the other name for white column? It was a fun name. Funiculus. And plural? Funicula. So white columns consist of multiple tracts, or you could say funiculi consist of multiple fasciculi. Each funiculus is going to have multiple fasciculi. I'm going to say it again. A white column can be divided into tracts. And then I'll say the same thing a different way. A funiculus can be divided into fasciculi. How many glial cells in the CNS?
4.
Which one contributes to the blood-brain barrier? Astrocytes. Ependymal line the choroid plexus, the interior surface of the ventricles, but yeah, it separates the CSF from the brain tissue, essentially. What do ependymal cells have to help them circulate CSF? Ependymal cells, like epithelial cells, don't function in isolation. You need them connected into a sheet. What's that sheet called of ependymal cells? Ependyma. So ependyma lines the ventricles of the brain and also lines the what of the spinal cord? Central canal. Central canal. Which glial cells form a 3-dimensional scaffolding or framework to hold all the blood vessels and all the neurons in place? Kind of like a skeleton. Astrocytes, specifically fibrous astrocytes, but just astrocytes is fine. Which glial cells in the CNS mop up excess potassium ions as they accumulate outside of the neurons?
Microglia.
No? Astrocytes.
Oh,
That was a trick question.
They do like everything.
so if we don't in doubt.
Well, here, do this. Know the one thing that each of the other 3 do, and then you know everything else is astrocytes. So ependyma do one thing, right? They're associated with CSF. Right? They separate it from the tissue, they circulate with their cilia, but it all has to do with CSF. Microglia, really just one thing. Defense. Immune. Right? That's your in-house immune cell for nervous tissue.
I thought that the microglia had something to do with mopping up debris and that kind of stuff, right?
We can check.
Am I crazy or?
Oh, I could be crazy. Wouldn't be the first time.
Or am I
Should crack without trying to go.
What is the muscle right here?
Let's just
Corrugator supercilium?
supercilium.
I'm closer.
Astrocyte. Maintain normal ECF potassium concentration, mopping up excess potassium.
Okay.
It said that for astrocytes, true.
All right, and then for oligodendron, what's really yeah? Huh?
So, can you hear?
No.
Yeah.
Mop up excess potassium from outside the nerve. Potassium.
Yeah, but I was thinking the same thing. Just the,
Oh, you're thinking like mop up debris?
yeah.
No.
Okay.
So
Good thing we clarified that.
can we change that on the study guide to like Swiffer? It says potassium.
You don't like mop?
No, because it's used.
Outdated.
It's used in the 2 things. That's why I think some of us were like.
The mop
but we-
the mop word's not used twice.
I thought it was.
Uh-uh.
Okay. Well, it's still outdated.
Roomba. Change it to Roomba. Swiffer's outdated.
Yeah. No, you're right.
Alright, and, yeah, question.
So astrocytes mop up the extracells.
Yes. And do you have your Google cells? Alright, the one thing oligodendrocytes do.
Their processes around.
Up to 16.
They myelinate
Myelinate
axons
in the CNS.
in
The
The
CNS.
CNS.
If we
And
end,
Schwann cells do it in the.
PNS.
if we answer like that,
Myelinate
is that
axons.
right?
one wraps itself.
If I call you over, if I do this and then, right?
And then I'll laugh and give a chuckle and then I'll say that.
Yeah.
Because it's
Are you guys done dancing?
Those are the two questions I'm for sure gonna get right now. Thanks to you.
You're welcome.
That's awesome.
What do you call the segment between nodes of Ron-VA?
Internode.
Internode. It's the myelinated part. And the node of Ron-VA is the bare part. What is not found along the internode? No, it has
No, it has
myelin.
myelin.
And because it has myelin, what is not occurring along the internode? What is not found there? Voltage-gated ion channels. So we describe the action potential as jumping from node to node. What type of conduction is that called? Saltatory. Saltatory conduction. As though it jumps from node to node. It's on there. The word's on there, I promise. Control F on the computer, saltatory. It's easier than Control F.
So what is it? Saltatory again?
Saltatory conduction.
What is that again?
So we're talking about a myelinated axon
Okay.
where the voltage-gated ion channels that regenerate the action potential are only at the nodes of Ron-VA. So it's described as though the action potential jumps from node to node.
Okay.
That's what saltatory means.
Okay.
What's the opposite of that? The axon that has no myelin. Continuous or contiguous propagation or conduction. What's the benefit of an unmyelinated axon using contiguous propagation? Space. Space is the upside. Right? Because we're talking mostly type C neurons, which not only are unmyelinated, but have the smallest axons. They take up very little space. We can pack a lot into a small area.
How would you draw the saltatory?
Oh, you don't have to. There's a slide
This is like
that shows it absolutely. Now, what's the downside to having myelin? Takes up space. There's another downside though. Demyelinating diseases. They only affect myelinated axons. That's right. What's the upside to myelinated axons? Saltatory conduction.
Faster AP conduction.
Fast and less costly. Less ATP required. Why?
Myelin helps.
If there's less channels that you have to open, that's less ion that you have to move across the membrane down its ECG, which in turn means less ion you have to pump back to where it came from, and that's where it costs ATP, pumping those ions back. So fewer channels have to open, fewer influxes and effluxes of those two ions, less pumping required to maintain normal concentrations. Right? So it's faster and it's less expensive, but it takes up a lot of space. And affected by demyelinating diseases. What's the loophole that some viruses have discovered for getting into the brain or spinal cord tissue without having to cross the blood-brain barrier? Retrograde axoplasmic transport. So they get into the end of an axon that's out in the periphery, where there is no blood-brain barrier, travel through the axon into the brain or spinal cord, and then come out at the cell body.
Retrograde what again?
Axoplasmic transport. Axonal transport is fine too.
That's a cute little guy that walks, right?
Yeah, the cute guy that
The kinesin that walks along.
carries things.
What are the two glial cells of the peripheral nervous system? Schwann and satellite. What CNS glial cell does the satellite cell resemble in terms of its function? Astrocytes. For example, both mop up excess ions around the neuron. Now, what do the satellite cells surround? Not just the neurons specifically, the bodies of neurons in the CNS. So if you want to see a satellite cell, you need to magnify a cell body, like a unipolar neuron. In fact, the picture that we saw, the histology image that we saw for the satellite cells came from the dorsal root ganglia. Right? So the DRG has a bunch of cell bodies in it. They're in the peripheral nervous system, so they're surrounded by satellite cells. And these cell bodies belong to what class of neuron? Unipolar sensory, right? What's another term for motor? Like a motor neuron? Efferent. Another name for sensory? Afferent. What receptors provide you with awareness of your body position in space? Proprioceptors. Where do you find them? Muscles, tendons, joints. Musculoskeletal system.
Any questions?
What?
Any questions? Go on.
The usual. What types of summation occur at postsynaptic membranes? Summation. What types of summation can occur at a postsynaptic membrane? Spatial and temporal. So if what you're looking at is the activity of one synapse over time, and whether or not it's active enough to accumulate neurotransmitter and generate a really strong graded potential, what type of summation is that? You're just looking at one synapse. And it's releasing neurotransmitter again and again and again, and then it builds. It's kind of like twitch summation. You release neurotransmitter, you get your graded potential, but before it's gone, you release more, and you release more. Spatial summation.
Because it's like a spaz.
No, that's Joey. Temporal. One synapse over time. Temporal, time. Temporal. What if you're looking at three synapses at the same moment in time? Spatial. Now with spatial summation, you can have some EPSPs and you can have some IPSPs, and you have to add them all together and see what the net result is going to be. Right?
So on the study guide, so I don't mean to interrupt, but on the study guide, there was something about multiple axons releasing their neurotransmitter onto one soma, right? One cell body.
Okay.
That was temporal.
Spatial.
That was spatial. That's the thing that keeps confusing me.
So let's just boil it down as simple as possible. One synapse, temporal. Multiple synapses, spatial.
One synapse,
Easy as we can put it.
spatial, and then temporal was multiple synapses.
Other way.
Okay.
One synapse is temporal. Multiple synapses is spatial. So if you're just looking at one synapse over time, temporal. Multiple synapses at the same time, spatial. What type of sensory information are you aware of? We essentially have three types. We have visceral, we have somatic, and we have special senses. What are you aware of? Somatic and special. And
Well, and two
visceral if pain or pressure. But generally speaking, you're not aware of visceral sensory input.
gas.
So, spatial is like the staircase effect, and then temporal is just one.
It can also be a staircase effect.
Okay.
Yeah, just a different reason.
Okay.
Absolutely. Who provides blood flow to the brain? Start basic. Arteries or veins? Provides blood flow.
Artery.
Arteries. Which ones?
Carotid.
Vertebral?
Yep. Carotid and vertebral. And if we want to be specific, internal carotid. Because external carotid takes care of the face, everything outside of the cranium. Internal goes into the cranium.
So internal carotid artery and
Vertebral. Drainage.
Internal jugular veins.
So jugular veins and dural sinuses. All right, what forms or what encloses the dural sinuses? Encloses them. Dural folds. What forms the dural fold?
2 layers of,
2 layers of meningeal dura. What are the names of the dural folds?
falx cerebelli and
Tentorium cerebelli. Falx cerebri, falx cerebelli, tentorium cerebelli. 3 dural folds. What vessel is at the very top of the falx cerebri?
superior sagittal sinus.
Right, and at the very bottom of falx cerebri. Mhm.
now I know.
And we didn't get into the other sinuses because I was saving that for next semester. But the transverse sinuses, those are in the tentorium cerebelli, and there's others. Oh, in what space do you find falx cerebri?
Spinal fissure.
In what space do you find tentorium cerebelli? What does the size of the homunculus represent in the primary somatosensory cortex? So I said sensory cortex and you said motor units. So the homunculus is not proportional. What parts of the homunculus are largest for the sensory and the motor homunculus? Face and hands. So in the because there's different reasons. So in the sensory homunculus, primary somatosensory cortex, you have the homunculus. What does that tell you? That the hands and face take up half the space, just the hands and face alone. Yeah, nerve endings, receptors. There's a lot more receptors in those areas of the body, and primarily we're talking about skin.
Which are type C nerves.
Say what?
Those. Forget it. Move on.
Forgotten. Type A somatic sensory.
Move it on.
It's all good.
That's why I will fail.
Oh, no.
Motor cortex, hands, face, again take up a lot of space. What does that tell you? The muscles of the hands and face are not big muscles, but they have a ton of motor units, which allows for what? Fine motor control. You have a lot of adjustment that you can make to the force output, very fine adjustments to the force output, but not so much with the big muscles that move the hips, knees, shoulder, and so on. What were the 2 functional brain systems we talked about? Limbic system and reticular formation. In a word or 2, what's the function of the limbic system? What does it provide? Emotion. Yes, known as the affective brain.
If you said association, would that be wrong?
That would be right.
That would be okay.
What part of the limbic system manifests your emotional state, what you're feeling, into a physical response? Hypothalamus. And what is the hypothalamus the boss of? And this is how it creates these physical responses. It's the boss of the autonomic nervous system. And it's the autonomic nervous system, specifically the sympathetic division, that's doing all those things when you're really anxious, nervous, scared. The flushing of your face, the nervous voice, trembling hands, sweaty palms, dilated pupils, all of that. Increased breathing, increased heart rate. That's all coming from the sympathetic division of the ANS, and that's coming from the hypothalamus. So literally, hypothalamus is sending signals through the pre and post sympathetic ganglionic neurons to create these responses. What areas of the brain are involved in controlling motor output? And I'm talking somatic motor output, skeletal muscles. What areas of the brain? In all. Voluntary, involuntary, just what parts of the brain are involved in controlling skeletal muscles? Primary motor cortex, premotor cortex, a lot more. Basal nuclei, brainstem nuclei, cerebellum. Of those, which one fine-tunes complex motor tasks while they're happening?
Cerebellum.
Cerebellum. Which one is important for initiating and stopping movements and making sure antagonistic muscles are quiet while the agonists do their thing? Basal nuclei. When the basal nuclei are not functioning properly and you get the symptoms of Parkinson's disease, where is the actual problem? Which neurons are degenerating in this scenario? Right, it's not the basal nuclei neurons, they're fine. It's the substantia nigra neurons who release dopamine to provide IPSPs, inhibitory inputs, to the basal nuclei neurons. And without the inhibition, they become overactive. And then that's what produces all the signs and symptoms. Shuffling gait, stiff movements, intense thought and concentration required to perform pretty simple tasks, tying a shoe, grabbing something out of the fridge. If you have damage to your left primary motor cortex, what's the consequence going to be? No voluntary control over muscles on the right side of the body. How about involuntary control? Still intact if you damage the primary motor cortex? Absolutely. Right, so, for example, if you were asked to extend your right knee and you've damaged the left primary motor cortex, you can't do that voluntarily, but if the physician takes the little rubber hammer and taps the patellar tendon and your knee kicks out, well, the quadriceps are doing that, right? So we can still control those muscles, but reflexively, subconsciously, no longer at a voluntary level. What if the premotor cortex is damaged? Primary is okay. What's the problem? Complex motor movements are not coordinated, right? They're just a mess. You're like a toddler again. Right? Try tying your shoe, shooting the free, it's a mess. It doesn't work out. Because all the coordination, all the planning occurs in the premotor cortex. You can still contract your muscles with your primary motor, but you're not going to be able to create any purposeful, complex motor tasks.
So the
You're not going to be able to execute them.
The premotor cortex coordinates the movements, and the cerebellum fine-tunes those movements.
Yeah. Yeah. And there's also, maybe not fine-tuning, but certainly some input from basal nuclei. What would be an inhibitory neurotransmitter? And not by name necessarily, just what is it doing? Any neurotransmitter that's considered inhibitory, what is it doing when it binds to its receptor?
Making it more negative.
It's opening what type of channel? Chloride or potassium? And then yes, that ultimately results in an IPSP, but it starts with the channel. So inhibitory neurotransmitters open channels that either allow potassium efflux or chloride influx. Excitatory neurotransmitters open channels that allow for sodium influx and therefore generate EPSPs. Which cranial nerves attach to the pons?
Facial, abducens, and trigeminal.
5, 6, 7? And then 8, 9, 10, 11, 12 all attach to medulla. What's the name of 10?
Vegas.
Vegas? 8. Vestibulocochlear. Is that sensory, motor, or mixed? So cochlear provides special sense information in sound, and then vestibular is also special senses. It's sense of equilibrium or balance. So that's all sensory. How about 12? Hypoglossal. So it goes under the tongue and it controls the tongue muscles and it's motor. What 3 cranial nerves control the extrinsic eye muscles? Yep, 3. Abducens, 6. Trochlear, 4. Which 2 attach to the brain, midbrain? 3 and 4. Where do you find corpora quadrigemina?
Midbrain?
Yeah. Front, back, side,
Posterior?
back of the midbrain. What's that region called? That back surface to the midbrain. In a quadruped, it's not the back surface, it's the top surface. Right? In a biped, it's the back surface. Tectum, which means roof. Right? In a quadruped, it's like this, and a human, it's like that. So it's the posterior wall for us. It's the superior roof for a quadruped. So everything else besides the tectum is what in the midbrain? Also starts with a T. Tegmentum. Tegmentum. What structures form the tectum? Tectum's an area, tegmentum's an area, but then we have structures. The collicula, yeah. So you could say corpora quadrigemina, but then we can separate it into the superior colliculi and the inferior colliculi. And then what reflex is carried out by superior colliculus? Visual. And inferior? Auditory or startle. Where do you find nucleus gracilis and nucleus cuneatus? Where? Sorry? Medulla, that's right. What information do they receive? Both of them collectively. Somatic sensory. Yeah, somatic sensory from the limbs. Upper limb goes to cuneatus, lower limb goes to gracilis. Where does the visceral sensory information go within the medulla? Which nucleus? It's lonely. It's a lonely nucleus. You want? I'm sorry. We'll talk afterwards. Solitary. The acronym? NTS. Nucleus Tractus Solitarius. So NTS or solitary nucleus.
Just put lonely on the exam and we'll know.
See, these little things help.
Solitary, lonely,
Yeah.
no, get that connection.
How about proprioceptive input? What nucleus in the medulla receives proprioceptive input? It's a food. Olivary nuclei. Within the olive, right? Those bulges on the front side of the medulla, those are the olives. What cranial nerves surround the olive? So lateral to it is 9 and 10, and medial to it is 12. 11 is lateral, but a little bit inferior. What brain region is an example of lateralization and is involved in language? That's one name, general interpretive area. The other? Wernicke's. Yep. What two nuclei in the midbrain have a distinct color? Red nucleus and substantia nigra. What neurotransmitter is being secreted from the substantia nigra neurons? Dopamine. What makes the red nucleus red? Rich blood supply along with iron-containing pigment. And then there's a really dark brown, almost black pigment in substantia nigra. How does CSF get from the lateral ventricle to the third? Lateral to third. Interventricular foramen. If you make a cross section through the midbrain, what part of the ventricular system will you cut through? What will you see in that cross section of the midbrain? It's not a ventricle, it's connecting ventricles. It's a connecting piece. Mesencephalic or cerebral aqueduct. Exactly. What is in front of the fourth ventricle? What forms the anterior wall of the fourth ventricle? Pons, mostly pons, yep, a little bit of medulla. What forms the posterior wall of the fourth ventricle? Cerebellum. What is running laterally on either side of the fourth ventricle, connecting the brainstem to the cerebellum? Cerebellar peduncle. Which cerebellar peduncle connects the midbrain to the cerebellum? Superior. Which one connects medulla to cerebellum? Inferior. And connecting pons to cerebellum, which is the biggest one? Middle. So all those transverse fibers that you see on the surface of the pons, they're headed back through the middle cerebellar peduncle to the cerebellum. The fibers that run deep through the pons, so the surface ones are running transverse. Through the deep pons, those are projection fibers. And those include which neurons? Which neurons project down through the deep pons? Pyramidal cells, upper motor neurons, corticospinal tract fibers, right? 3 different ways of describing the same thing. So if we start at the top in the primary motor cortex, name all the structures that that axon will pass through, the axon of the pyramidal cell. So first, corona radiata, then internal capsule. Not yet, gotta go past the midbrain first. So corona radiata takes us through the hemisphere. Internal capsule, we're now going on either side of the diencephalon. So what's right under the diencephalon? Midbrain. Diencephalon is thalamus, right, and hypothalamus. So right under the diencephalon midbrain, and so those structures on either side of the midbrain that contain the corticospinal tract, peduncles, cerebral peduncles, and then deep pons, and then medullary pyramids. And then it's at the pyramids that 85% of these corticospinal tract fibers cross over. What's that crossover point called? Decussation of the pyramids.
Decussation, right?
Decussation, which just means to cross. What disease is associated with heavy metal? more specifically, accumulation of heavy metals. Heavy metal poisoning.
I don't remember this at all.
It only affects myelinated axons.
Give us a hint.
It's a demyelinating disease.
Oh.
MS?
That's one.
Yeah. That's what I was
What
thinking.
was it?
Just demyelinating diseases.
What's it called?
One cause of demyelination is heavy metal poisoning. Chapter 11. What chemicals can be used to stop pain transmission? This would be something that you could even put on the gums of an infant when they're teething to block the pain receptors. So you can do this topically, you can inject it. When you have root canal done, fillings done, they inject this into the
Epidural?
lidocaine, benzocaine. Yep. How about the toxins from puffer fish that block voltage-gated sodium channels? Tetrodotoxins and saxitoxins. How are graded potentials different from action potentials? Let's go through as many differences as you can come up with.
Action potential.
They can be summed.
Action.
They don't just regenerate, potential.
This law of decay over time.
They decay. So we're just talk about graded potentials, but what you're giving me are things that are different from action potentials. So graded potentials do decay over distance. They can vary in strength. They're produced by ligand-gated or mechanically gated ion channels. Which ions can they involve? Potassium, sodium, but that's not different from action potentials, but there is one that's different. Chloride, that's right. They can be depolarizing, which action potentials always are, or hyperpolarizing. Okay. You can deviate from rest in either direction. Action potential, always depolarizing. Where do you find graded potentials? Where do they occur? Locations.
Soma and the dendrites.
So postsynaptic membranes, soma, dendrites. Where else? Go back to something you've already learned, chapter 9. Motor end plates. And what's the name of the graded potential at the motor end plate? End plate potential. What's the name of the graded potential at a postsynaptic membrane, which is dendrite or cell body?